All right, guys. So now it's time for us to talk about periodic trends. Periodic trends are probably going to be a pretty important part of the AP test. We're going to want to make sure that we fully are understanding everything that the periodic table can tell us, because you always have the periodic table as a reference. So anytime you have a tool like that provides so much information, you know that the people that write those tests are going to be making sure that you understand all the information that is contained on that table. So we have a number of periodic trends that we're going to go through. This lesson will start to focus on the trend of atomic size, is the trend that we're going to be looking at today. And my board's not working, so give me a second. There we go. Let's see if it's working now. So atomic size is the one that we're going to be focusing on. Now, on your notes, you have a section there on atomic radius. That's what we're going to be working on for this one. You probably don't have enough room for the example, so I would very strongly suggest getting out a piece of paper, because we are going to be taking some notes and doing some examples, and I've kind of shoved everything onto this piece of paper for you here. So you might want to do those on a separate sheet. So let's start with first what atomic radius is. Atomic radius is the distance from the center of the nucleus, so over here, to the outermost electron. And remember, the outermost electron does move around, so it is an estimation, but it's a distance that's measuring how far it is from the center of the nucleus to the outermost electron. And this can be really important to us in bonding and whatnot, because it's going to tell us a lot about what's going on in our atom and how close the nucleus is, how the nucleus can pull things in. You're going to see this same concept in our other periodic trends as well. So the radius is what we're going to be looking at, and you can actually tell a lot about what the radius is going to be for an atom just simply by looking at the periodic table. So we're going to go through and look at the trends. You have a diagram similar to this on your paper. Yours is a little different, but it's still the exact same information. You can see that in general, as we go down a group, atoms get larger. And if you are thinking right to left, you're getting larger. If we're thinking like the United States, we always read from the left side to the right side. You can think of them as getting smaller, but this diagram shows you the getting larger direction. On your paper, you can see the same information. So atomic radius increases as you go to the left on the periodic table, and it increases as you go down. And we're going to talk about both of those trends and why they are the way that they are, because we should be able to look at two things on the periodic table and be able to tell which one's bigger than the other one based on where they're located on the periodic table. So the trends, here's the first one. Oh, by the way, I absolutely despise periodic trends in that I don't like that students try to make general statements and don't truly understand. So you'll see here the general statement that atoms get larger as you move down a group, but that doesn't show that you understand anything. So if I ever ask you why one atom is bigger than another and you just say they get larger as they move down the group, I am not going to give you points. You need to explain why, as you move down a group on the periodic table, why are the radii getting larger? What makes that occur? And the why you have there on your paper. The reason is because as we move down the periodic table, down a group on the periodic table, you're going to higher and higher principal energy levels. And that means those electrons are going to be further and further away from the nucleus. Remember, if you remember from last year, our analogy of the apartment complex, you have a first floor, a second floor, a third floor, etc. Same thing here. As you go up an apartment complex, you're getting further from, ground level. Same thing with the atom. You're getting further away from the nucleus. So the atom's getting bigger and bigger and bigger. If you look at the periodic table that you have on your paper, for example, lithium and sodium. Lithium's valence electrons are on the second energy level, whereas sodium's are on the third energy level. So it has to be that sodium's bigger. It has to be. No matter what, that one has to be a larger nucleus, a larger radius from the center of the nucleus to that outermost electron. So as you move down a group, the reason is because the valence electrons are on higher energy, principal energy levels. And that's true of all your groups as you move down them. So don't learn the trend. You can use the trend as like a help, but don't learn the trend, learn the why. The why is the important part. All right, the second trend, which again I don't like, is that atoms will get smaller as you move from left to right, or if you want to think of it how the diagram is showing you, you can say atoms get bigger as you move from right to left across a period. And this one actually contradicts what a lot of people think, because as you're moving across a period, for example, look at your periodic table, maybe look at carbon and oxygen. A lot of people think oxygen will be bigger because it has more protons. But remember, we're not talking about protons in the nucleus here. We're talking about the radius to that outermost electron. And so what you have to be thinking about is what effect does having more protons in the nucleus have? So if you take a look at the reason why it gets smaller is as you move from left to right across the periodic table, you have more protons in the nucleus. Same energy level, okay, they're on the same energy level if we're comparing across the period, but there's more protons in the nucleus. More protons pull in more tightly and make that nucleus sort of shrink up. And when it shrinks up, you're going to have a smaller distance from the center of the nucleus to that outermost electron. So as you move across the period from left to right, atoms will get smaller because you're getting more and more protons in the nucleus. Okay? So again, why is important, not the trend. So make sure you understand the why. You don't even need the trend if you understand the why. So within the same energy level, this will definitely be true. Now, there's an issue with that method. And the reason why there's an issue with that method is, what if I was asking you to compare, say, nitrogen and sulfur. Find nitrogen and sulfur, please. So we said that the bigger one will be the one that's further down. So that would be sulfur, right? Because it's third energy level, nitrogen second energy level. But then we also said the one further to the right would be smaller, and sulfur's the smaller one then because it would be further to the right. So we really need to be thinking about this logically. That last trend, if we get back to it, it was saying within the same energy level that was true. But if you're on different energy levels, how are you supposed to decide what's going on? What if they're not on the same group or the same period? How are we going to figure this out? Well, down at the bottom of your paper, so skip over the ionic radius part. This bottom part applies to both ionic and atomic radius, but skip over the ionic radius part, go to the bottom. This is the method I want you using. So I want you to get a highlighter out or your pen or pencil and circle, mark it up, star it up. This is how you should be doing these trends. This is the way that it's going to end up making sense and be logical and be a way that you are going to maximize your points. The way that you should look at any comparison, so you've got two elements. They're giving you two elements, say nitrogen and sulfur, that we were just looking at. The first thing you want to look at is what the valence energy level is. If they are on different valence energy levels, that will immediately tell you which one's bigger or smaller. Again, nitrogen and sulfur. Nitrogen is on second energy level for its valence electrons. Sulfurs are on the third valence energy level. So sulfur has to be bigger. End of story. So the higher the principal energy level, the bigger the atom. So if that's the case, then you're done. You don't have to look at anything else if they're on different valence energy levels. Okay, that you're really happy, by the way, when that happens, because then it doesn't require any more thought. Now, if they are on the same valence energy level, so for example, let's say we were looking at calcium, number 20, and bromine, number 35. Calcium and bromine. So if they are on the same valence energy level, then obviously this didn't help us. Okay, and number 1 is the most important. You always look at number 1 first, but it didn't help us. So then we're going to go to number 2, and we're going to look at the number of protons in the nucleus. And again, we only do this if needed, but if we're trying to compare calcium and bromine, then it is needed. So we look at the protons. Calcium has 20 protons in its nucleus. Bromine has 35. So 35 is more, and the more protons you have, the smaller the atom's going to be, as we described above on number 2 of the trends. More protons means more inward pulling, and you do need to explain that inward pulling. Don't just say more protons is a smaller atom. I just have it summarized here. Use the thought from the trend above that more protons means more pulling, and those electrons get pulled in more tightly to that nucleus. Now there is a third part there you can see to look at electrons, but that's not going to apply until we get to the atomic radius one. Okay, so we'll come back, the ionic radius one. We'll come back to that when we're doing ionic radius. But for atomic radius, because we're dealing with atoms that are neutral, we know that these are going to be the only two factors that we're ever going to have to look at. Either they're on the same energy level and you look at protons, or they're not on the same energy level and you've got it figured out without any need for anything else with that. Okay, and I'm going to skip through this one and we'll come back to that one later. Okay, so let's try an example or two and see if you are understanding. So start with sulfur and oxygen. Sulfur and oxygen. Go ahead and pause the video and determine which one it is and explain why. Explain why the larger one's the larger one, and then hit play again. All right, so for sulfur and oxygen, you should have come up with sulfur as the larger one, because if you look, sulfur is on the third valence energy level, whereas oxygen's only on the second. So it's going to be the larger atom because its valence electrons are further from the nucleus. Okay, let's try another one. Which one's the larger atom? Either F or SE. F or SE. pause it. Okay, so for F and SE, you should have said SE, because if you look, F is on the second energy level and SE is on the fourth energy level. So SE has to be the larger atom out of those two. Okay, next example. I don't know why I'm doing all larger. I could ask you smaller, by the way. But which one's larger, carbon or oxygen? Now, immediately, before you pause me, immediately you'll see they're both on the same valence energy level. So think about the fact they're same valence energy level. Go ahead and pause the video. All right, so for carbon and oxygen, you should have picked carbon as being the bigger one because oxygen has more protons in its nucleus. So that one's going to be pulling its electrons in more tightly. You can explain that, by the way, using oxygen like I just did, or on the screen here you can see that I said carbon because they're on the same energy level, so the one with fewer protons will be larger. This part right here is very important. Let's see, right here. They're on the same energy level. That needs to be in your description when you are using protons as your reason. You have to show that you looked at the first rule, which was energy level. So you have to state in your little description they're on the same energy level and then discuss the protons. Okay, don't ever just start discussing the protons. Make sure you say that they are on the same valence energy level. That's often worth a whole point. And if you don't say it and you go right to protons, you lose that point, and we don't want that to happen, obviously. All right, so that is the end of atomic radius. Ionic radius is very similar, but we'll cover that as a separate lesson. And so you're going to do some examples and some practice with this so you can keep working on it. But again, that bottom section of the notes is what you should be most concerned with when you're trying to do your reasoning of your periodic trends. All right, time for trend number 2, ionic size. The beauty of ionic size is it really is a lot like the one we already did for atomic size. I like to think of them really as the same set of rules. Remember, we said down at the bottom of our paper is a set of rules that are going to govern size. It doesn't have to be atomic, or it doesn't have to only be atomic or only ionic. It governs both of them. There are some trends that go along with ionic size, and I am going to show them to you just because they help explain a little bit. But I really want you focusing on those three rules down at the bottom, and we'll get to the third rule with this lesson because last time we only talked about the first two, so that you can fully understand this. But let's go ahead and take a peek at what we're dealing with here. Okay. So ionic radius, first of all, is almost identical to atomic radius, except it's an ion. Atomic radius versus ionic radius. It's an ion, meaning it has either gained or lost electrons, but it's still the distance from the center of the nucleus to the outermost electron. The only difference is this word ion here as opposed to atom. So we're still measuring the same thing, and that's why the same rules are really going to apply. Now, I need to make sure that you remember two terms from last year, and if you don't, make sure you commit these to memory. The first one is the term cation. A cation is a type of ion that's lost electrons, meaning it has a positive charge. So like Ca+2 would be a cation, or H+1 would be a cation. Anything with a positive charge is a cation, and the opposite of that is an anion. An anion is something that has gained electrons and therefore has a negative charge. Now we're going to get into the trends, and again, I told you before, I hate trends. Please don't ever quote this trend, even though I'm showing it to you. I don't want you to use the trends. I want you to use thought. I want you to actually think about what's happening and not just immediately go to, oh, cations are always smaller than their parent atoms, okay? But it is true that cations will be smaller than their parent atoms. So you see here an example of sodium atom and then a sodium with a +1. So we're going to go through and discuss why this may be the case. And there really can be two reasons for this. And you can see you've got these reasons listed on your paper. The first is a lot of times when an electron's lost by an atom, it loses the valence electrons that it had, the outermost energy electrons that it had, like sodium. If you look at sodium, this one that we had right here, sodium has one valence electron on the outermost energy level. If you write the electron configuration for sodium, it ends 3s1. So if it loses that one electron and becomes sodium with a +1 charge, it's really behaving like neon. It's really got 10 electrons, and so electron-wise, it only has those 10 electrons, still same number of protons, and so we're going to get a smaller atom. So if it loses the only valence electrons it has on a shell, then obviously it's dropping a whole shell. That's definitely going to make it smaller. If that doesn't happen, because it might not lose enough to drop the whole shell, which is very uncommon, but if you lose electrons, no matter what the situation is, you're going to get less electron-electron repulsion. We know electrons don't like to be near each other. So when you have an electron in a shell with another one, they are always going to maximize their distance away from each other. So every time you pull one out, the other electrons get to relax a little bit and not be so repulsive against each other. And that would cause it to get a little bit smaller. I will tell you most of the time it's this reason, is the reason. And again, our three things down at the bottom are going to explain this in a way I think is even more logical than just using this. But I do want to show you the trends and how they are. So sodium versus sodium plus 1, the one I was just using it as an example. So you see sodium has a 3s1 electron. Well, if we lose this electron, now the electron configuration is 1s2, 2s2, 2p6. The only valence electrons are on the second energy level now. You dropped a whole energy level. It has to be smaller. And that's just the rationale behind the majority of these and how they work. Now, although, so you lost the only electron on third energy level, so now the second energy level is going to be its smallest. I've got another example here, although I don't really like this example because why would magnesium be a +1? I mean, it doesn't want to be a +1. It either wants to be a +2 or just be itself, you know, an atom of magnesium. But just so you can see the other rationale, so if magnesium has 2 electrons in its valence energy level, if it becomes Mg +1, then now it only has 1. So this electron isn't repelling this other one as much anymore, so it can come a little closer to the nucleus. And that is the reasoning behind that one. All right, now the second trend is anions. So if you have an anion will always be larger than their parent atom, okay? And if you think about that, hopefully it's kind of clicking into your head after seeing the last one as to why that would be. So if we have something like chlorine and it gains an electron, you're putting an extra electron on that energy level. Do electrons like to be near each other? No. And so what are they going to do? They're going to repel and they're going to push outward to try to get away from each other. And that is the reason why anions will end up always being larger, because there will be an increase in this electron-electron repulsion. Okay, so there's the short version as to why they are the way that they are. You can see through their electron configurations here. So chlorine had 5 electrons on the outermost energy level. Now if you gain one, you get a -1 charge. Now you have 6. More electrons, more repulsion. That's the reasoning behind the whole trend. Now, again, those are the trends. I don't really like the trends. The trends will help you solve problems like these ones. So let's go ahead and we'll solve these 2 problems, and then I'll show you how they're not going to help you on other problems. So go ahead on these 2 problems, pause the video, and figure out which one will be smaller in each of the pairs and the reason why. We always write the reason why. Pause the video. Okay, so for number 1, you should have said Ca plus 2, and the reason for that is because you were losing the 2 most valence electrons, and so you were dropping down an entire energy level. Okay, calcium with a +2 charge is acting like argon. Okay, so energy level wise, it is on the same energy level as argon is. Now S and S-2, you should have picked S as the smaller one because S-2 has more electrons than S, and if it has more electrons, you'll be repelling more. But again, to me, that's confusing. To me, that takes more thought than is necessary, because those 3 principles we have down at the bottom of our paper would have taken care of these 2 and helped us on problems where it's not just the parent atom. What if I ask you to compare, say, O with a -2 to S with a -2? They're different atoms, so you have to be looking at other factors to be able to see how their ions are going to be behaving. And so that's going to bring us back to those 3 things down at the bottom of your paper. We said the first thing we're going to always look at is the energy level, and that will still be true. We'll definitely look at the energy level. If there's a difference in energy level, that answers your question. And then the second thing we're going to look at is the number of protons. Like we said before, more protons means a smaller atom because there's more inward pulling. And then the last thing we're going to look at is the number of electrons. Now don't look at electrons unless number 1 and number 2 have told you the exact same thing. So you would have to have, say, Fe with a +2 charge being compared to Fe with a +3 charge, because they have to have the same number of protons and the same energy level for us to even care about number 3. So we very rarely get to number 3. But if we do, it's going to be a matter of more electrons causes more repulsion. Okay, if we have more electrons, there's going to be more electron-electron repulsion. So let me show you some examples of this, and then we will do some more together as well. So let's say we have Rb with a +1, and we have S with a -2. Find Rb with a +1 on the periodic table. Rb with a +1 isn't Rb anymore, right? It's krypton. Electron-wise, it's acting like krypton. So its valence energy level is the 4th energy level. Okay, so this one's got valence electrons on the 4th energy level. For S-2, you're going to have sulfur, which is 16, but -2 means it's acting like argon, so that's going to be 3rd energy level. So 4th energy level versus 3rd energy level, I don't have to go any further. I know that rubidium is going to end up being, oops, sorry, there's some more examples here. Rubidium is going to end up being the larger one of those two because its valence electrons are on the 4th energy level. Okay, so that is the whole process that you're going to go through. Now on your paper, I want you to do these other 3 problems, and I want you to bring them with you to class so that we can take a look at them and make sure that your rationale is right. Again, you need to decide which one's larger out of the pair, okay, using the 3 principles that are at the bottom of your notes, and give the reason. Okay, and the reason is going to be very important and a very important part for us to look at and make sure we're fully understanding.